Here in this section, we're going to look at the sum and difference identities for both sine and for tangent. The sine identities look very similar to the cosine identities for sum and difference. However, we notice that there's some slight differences that we want to be careful to note. When we have sine of a sum, we will start with sine and we will end with sine, and cosine will be kind of hugged in the middle. Sine, if there's a plus, sine keeps the same sign, so that will also be plus. When we look at the difference of two angles inside of sine, if there's a minus sign on the inside, there's also a minus sign on the outside. So sine keeps the same sign. So if we wanted to go and look at this being used, we have sine of 105, sine of 105 degrees. So we can think about this as an unknown angle, something we don't know. We're not familiar with the sine of this angle, but we can think about this as the sum or the difference of two angles that we are already familiar with. So I'm going to think about this, and any two angles that you can think of that add or subtract to give you 105 will work. We're going to use angles though that we are familiar with, so let's use angles like 60 and 45 degrees. So if I add 60 plus 45, we get 105. So make sure that you're using angles that you are familiar with. We need to know, without a calculator, what the sine and cosine values of both of those angles are. So let's use our identity. It's going to be sine of the first angle, cosine of the second angle. Sine keeps the same sign, so we're going to use plus. Cosine of the first angle times sine of the second angle. Sine of 60 degrees is square root of 3 over 2. Cosine of 45 degrees is square root of 2 over 2. Plus cosine of 60 would be 1/2. Sine of 45, square root of 2 over 2. Very, very similar process to the identities for cosine. And our values even look similar. We have square root of 3 times the square root of 2. That would be square root of 6. 2 times 2 is 4. Multiply across the two fractions. Plus square root of 2 over 4. We're going to combine the fractions, keep the same denominator, combine the numerators on top. So while we were not familiar with the sine of 105 degrees, if we use angles that we are familiar with, we can derive that sine value of 105 degrees. So this would be considered to be the exact value, and you could put that in your calculator also to find an approximation. We are asked to find the exact value of tangent of 15 degrees without using a calculator. So we want to use either a sum or a difference identity for tangent. So let's rewrite 15 degrees. Let's rewrite the input angle as two angles that we are familiar with, either added or subtracted to obtain 15 degrees. So any two angles that you know, so what about, let's see, 45 minus 30 degrees. So keep it simple. Any two angles that add or subtract to give you 15 degrees will work and give you the correct answer. So we're going to use 45 degrees minus 30 degrees. The identity for tangent, we're going to use the difference identity. That would be tangent of the first angle minus tangent of the second angle divided by 1 plus tangent of the first angle times tangent of the second angle. Now tangent of 45 degrees is 1 minus tangent of 30 degrees is square root of 3 over 3 divided by 1 plus tangent of 45 degrees is 1 times tangent of 30 degrees, square root of 3 over 3. So we have this complex fraction, and we would like to simplify the complex fraction. Let's do that by multiplying by the LCD of all of the little parts here. And it looks like the LCD would be 3. And that would give us 3 minus the square root of 3, since the 3's would cancel. 3 plus the square root of 3. Now if you want to go further and get rid of the radical in the denominator, you could also do that, depending on how far you would like to simplify. If you want to get rid of the radical in the denominator, you would multiply by the conjugate of the denominator. And the conjugate is just the same number but opposite sign. So the same exact binomial except opposite sign in the middle. And then you would have to FOIL. So we'd have to FOIL on top, FOIL on the bottom. So first times the first, that would give 9. Outer times the outer, that would be 3 square root of 3. Inner times the inner, that would be another negative 3 square root of 3. And then last times the last, we get positive square root of 3 times square root of 3 would be 3. All over, and then on the bottom we're going to get something very similar, except the middle two terms will end up canceling out because conjugates always have the two middle terms cancel out. So we end up with 3 times 3, which is 9, and then last times last, which would be negative 3. So when we simplify, we get 9 minus 6 square root of 3. Actually, let's combine those like terms. Since we have 9 and positive 3, let's write that as 12. And then negative the square root of 3, negative square root of 3 would be minus 6 square root of 3. All over, and we have 9 minus 3, that would be 6. And once again, depending on how far we want to simplify, we can keep going. We have a common factor of 6 between all of these terms. 6 goes into 12 2 times. 6 goes into 6 once, so that would be minus square root of 3. So we could do that division there, and we could simplify this whole thing to be 2 minus the square root of 3. In example 2, we want to use those sum and difference identities to write each expression as a single function of x or theta. For part A, we're given tangent of pi over 4 plus x. Right now, the argument or the input for that angle is a little bit more complicated than maybe we would like to work with. We would like to get our argument or the input angle to be just x or just theta. And we can do this by using our sum identity for tangent. So tangent of pi over 4 plus x would be tangent of the first angle plus tangent of the second angle divided by 1 minus tangent of the first angle times tangent of the second angle. So when we simplify, pi over 4 is the same thing as 45 degrees, which makes this simplify very nicely. We get 1 plus tangent of x divided by 1 minus, and of course this becomes 1 times tangent x, so that's just 1 minus tangent x on the bottom. So now the input angle for tangent is just x, much simpler than the more complicated pi over 4 plus x argument or input angle that we started with. For this next part, we want to simplify using the difference identity for sine. So we want to recall what our difference formula for sine looks like. So we have sine comes first, sine of the first angle, and then the next thing is cosine of the second angle. Sine keeps the same sign, so if we're subtracting on the inside, we will be subtracting on the outside. And then cosine of the first angle times sine of the second angle. So the sine formula starts with sine and ends with sine and keeps the same sign in the middle. Now sine of 270, let's draw our unit circle and remember what point that we're using. That would be 0, minus -1, or minus 1. Sine of 270, that would be the y value. So that would be minus 1 times cosine theta, minus, and the x value would be the cosine value of 270, so that would be 0 times sine theta. Now we want to simplify. We're going to multiply and then do the subtraction. Negative 1 times cosine theta is minus cosine theta. And 0 times anything is always 0, so that's minus 0. So this entire expression simplifies just to be minus cosine theta. For part C, we would like to use the difference identity for cosine to simplify this expression. So cosine starts with cosine, so it's cosine of the first angle, and then cosine of the second angle. And then opposite sine, so for subtracting on the inside, we'll be adding on the outside. And now sine gets a turn, sine of the first angle times sine of the second angle. So we'll start to simplify cosine theta times cosine of 30 degrees, which would be square root of 3 over 2, plus sine theta times sine of 30 degrees, which would be 1/2. And we can simplify this a little bit more. Let's see, let's write this as square root of 3. Let's multiply across here. So we'll think about those both as fractions, then multiply across. Now we'll think about this as square root of 3 times cosine theta all over 2 plus, multiply across, we get sine theta times 1, which is just sine theta, and then 1 times 2, which is 2. So we get a common denominator, and so we can combine the numerators on top of that same denominator. Example 3, we want to verify that the equation is an identity. So we want to show that this is true for all angles S and T. So we're going to choose a side to start with. We're going to choose the left-hand side. It looks a little bit more complicated. And we are going to show that we can achieve the right-hand side. We're going to choose tangent S plus tangent T as our goal. So we're going to start with sine of S plus T. So we have a sum, and we're going to use that sum identity to rewrite sine of S plus T. So our sine identity, our sum identity for sine would be sine of S, and then cosine of T plus cosine of S times sine of T. All of that divided by the denominator cosine S times cosine T. So we have this one giant fraction. We would like to simplify this by stretching it out into two separate fractions. So right now we have two terms at the top, and they are sharing this denominator. So let's give them back their own separate denominators. So let's write it as sine S times cosine T. So we'll write the first term and give it back its own denominator of cosine S cosine T. And then we'll say plus, and then we'll give the second term, cosine S times sine T, we'll give it its own denominator as well. So we're going to give it back that denominator cosine s times cosine t. And we want to convince ourselves that this is equivalent to what we had in the previous step. If I was to take these two fractions and add them together, we would keep the same denominator and combine the numerators on top. So we can get back to the previous step very easily. So we want to make sure that we have an equivalent two fractions, equivalent to the previous step. And now we would like to simplify. So we see that now that we've separated it into two separate fractions, we have cosine t and cosine t, and we can cancel those common factors. And we're left with sine s over cosine s, which would be the same thing as tangent of the angle s. And then here we see that we have cosine s and cosine s on the top and the bottom, so we can cancel there. So we end up with sine t divided by cosine t, and this would be tangent of the angle t. And if we look back to our original goal, our goal was tangent s plus tangent t. So we have achieved our goal, and we have shown that the left side is equivalent to the right hand side.